with an invariant of closed n-dimensional objects, for instance, closed n-manifolds. And from that, we can build vector spaces for n-1 manifolds, for closed manifolds of dimension 1 less, and build suitable categories. So let us understand this in detail. So we're gonna work over some base field. For us, it's a field. You can later make it a commutative ring, and just things become a little bit more complicated. Mostly, it's a field for us. And we start with just assignment of numbers or elements of the field K to some n-dimensional objects. I don't know. Yeah, I can. Yeah, it looks like other people
are there any questions, dear colleagues? So please, if possible, I would like to ask you to mute your microphones unless you have questions to the speaker. So thank you for understanding.
Yeah, thank you. So, right, so we have, so we start with something very general. We start with any map from diffeomorphism classes of our objects, for instance, manifolds of dimension n, closed manifolds of dimension n, to elements of the ground field. So we have this map alpha from manifolds of dimension n to the ground field. And the only condition we impose on alpha is that it's multiplicative, in the sense that alpha of the disjoint union of two manifolds is the product of alphas, of invariants of individual manifolds. And we require that it's a function of diffeomorphism classes or suitable isomorphism classes. So if the objects of manifolds are diffeomorphic, we want the invariants to be equal. So that's all we require. So picture-wise, we start with a manifold or kind of manifold-like structure, something topological of fixed dimension n, and assign to it the invariant alpha m, an element of k. And we're going to look at low-dimensional cases where we can ignore orientation reversal. It's possible to add reversal of orientation using the usual story from TQFTs. We can add an additional involution on our field such that the invariant of the manifold with the reversed orientation is the involution psi applied to the invariant of the original manifold M. So it's easy to add this involution, but we won't need that. Essentially, in our examples, the involution is the identity, and the invariant of manifold M and manifold with reversed orientation, they don't differ. So given such a data, it's very general to close manifolds up to diffeomorphism assign numbers, and it's multiplicative. So we can reduce this to just assigning a number to every, assigning an element to the ground field to any connected oriented closed and manifold. So from this data, we can build invariants or state spaces for manifolds or manifolds with additional structure in one dimension lower, in dimension n-1. So let us fix. So here is the picture. So pick an n-1 manifold, n, and we're going to build a state space, assign a state space to n as follows. So first we look at all the manifolds of dimension n, m, all the manifolds of dimension lowercase n that bound n. So m such that dm is n. And we first form the free module over the field k with a basis of symbols of these manifolds. So in other words, elements, generators of this free module over k are manifolds m with boundary n. And so this is accountable. So it's accountable. Well, we can say up to. So that's a countable set if you look at this manifolds up to diffeomorphism. And so it's a vector space with a countable basis. And on this vector space, there's a canonical bilinear form. This bilinear form, it takes two vectors, two generators, m1 and 2, that bound n. so M1, M2 with the same boundary n. Now we can glue them together along n. So picture-wise, we can reflect M1 to be on the other side with the reverse orientation and glue it to M2 along common boundary n. So this is a closed n-manifold. You can apply alpha because remember alpha is an invariant of closed n-manifolds to take values in the ground field K. So for any pair of manifolds with boundary n with the same boundary gives us a number, an element of K. So it's alpha of the union of minus M1 and M2. And this is our bilinear pairing. And again, we're ignoring orientations. So for this reason, the pairing is symmetric. Alpha of minus the manifold is alpha of the manifold. Again, this is a kind of minor, additional minor thing to keep track of in high dimensions. But in low dimensions, there is kind of no difference. And in all our cases, minus m is diffeomorphic to m. So this way we get a bilinear form on this very large vector space, well, with a countable basis. If you look at manifolds up to diffeomorphism.
So colleagues, once again, if possible, I'm asking you to mute your microphones unless you have questions. Okay. Thank you for understanding.
So now, given this bilinear form, we can look at the kernel of this form. So kernel, and look at the kernel of this form. It's a subspace of the space freely generated by our manifolds with boundary, and they take the quotient and call it alpha of n. Call it the state space of n. So what does it mean to be in the kernel of this form? So a vector in the space free of n is in the kernel. Let's call this vector, denote this vector as some so symbols of mi's with boundary n times some coefficients lambda i's in the ground field. So a vector in here has this form. It's a finite combination of manifolds mi with boundary n with coefficients in the ground field K. So the sum belongs to the kernel, or the sum is 0 in the state space if the following holds. If no matter what m we choose with boundary n, so choose any m and attach it on the other side of n at the top. So here you have mi, here you have m. We can use alpha to evaluate this closed n-manifold. We get a number, an element of the field K. So now this sum is 0 in the quotient space if and only if for any m, this sum is 0 in the ground field. I mean, this is just the definition of the quotient space of the kernel. So this sum is in the kernel if and only if this holds. And that's a lot of conditions. That's a condition for every m that bounds manifold m. So there's lots of conditions. So if you choose your alpha, generically, so alpha is this map from closed and manifolds to the ground field. For generic alpha, it says here for generic alpha, the kernel is going to be 0 because it's too many conditions to hold if you pick. So picking your evaluation generically, typically will be no relations of this form. So for generic alpha, this kernel is 0, and in fact alpha n is this big space freely generated by manifolds with boundary n. So it's not that interesting. You have no relations. But what we want to do is look at the degenerate case when kernel is very large, such that, in fact, by very large, what we want is to look at degenerate alpha such that alpha n has finite dimension or finite rank our ground field. So for all manifolds n. So for all manifolds n of dimension n minus 1, we want the state space to be finite dimensional. So we want lots of relations. You can also think of this. You can think of these relations as sort of scaling relations. on manifolds with boundary, just saying that in the state space of n, we have this relation. So no matter how we cap it off, it's 0.
Do you have any examples of how this can evaluate to some?
Yes, we'll look at examples. We'll look at examples soon. It's in fact, this is quite close to TQFTs. So let me explain one difference, or the main difference from TQFTs. So the main difference is just like in TQFTs. So if you have two n-1 manifolds, n null and n1, right? So given m null that bounds n null, given m1 that bounds n1, we can put these cobordisms together next to each other to get disjoint union m null union and m1 that bounds m null union n1, and this gives you a map from the state space of a null tensor state space of n1 to the state space of a null union n1. It's a very easy exercise to check that this is well defined. But if you had a skein relation here on the SEMs, well, you're adding stuff on the side, you're capping it off, but this relation still hold. So it's very easy to see that first you can build a map define a map from free and null tensor free space of n1 into free space of a null union n1. But it's immediate that this descends down to the maps of state spaces. That's because once you have a skein relation, then no matter what else you add here, you're still going to have the same skein relation. So if you add something here and that you still have a skein relation on the side and a skein relation on this side. Consequently, you have this induced map. So the catch is that this map is usually, you can check it over a field. This map is injective. And this is just because in the state space, you can evaluate using cobordisms that are disjoint, a cobordism for a null and a cobordism for, you can close it up separately for a null, separately for n1. So you can have as many variations, so to speak, in here as in here, and possibly more. And because of this, the map is injective. So if something is 0 in here, it's going to be 0 in here as well, because you can just reduce to evaluating using disjoint cobordisms. But usually the map is not surjective in the sense that you can build cobordisms that connect n null and n1, and these cobordisms will not decompose into combinations of these cobordisms that are disjoint. We'll see examples. So usually this map is not surjective. And in this sense, it differs from a TQFT, because in a TQFT, these maps are isomorphisms in a TQFT. And again, so what happens, why is it not a TQFT? Because if you have n and minus n, you can create this tube, which is just a direct product of the n with the interval, turn bend so that it creates this cobordism. So usually, in most of the spheres, this tube is not equal to a linear combination of elements of this form, where you have a separate cobordism for n, separate not cobordism, but a manifold for n, a manifold for minus n with some coefficient, and I. So usually, and we'll look at examples, there is no such decomposition. And another way to say it, or we like to call this relations neck cutting relations, and you can take this tube and simplify, not simplify, but decompose in this form. So in TQFT, that's always possible. It's one of the axioms, but there is no such decomposition in this series alpha. As a result, the image of the tensor product of the state spaces for n null and 1 is usually not the entire space for the disjoint union. So it's not monoidal, but you can, maybe there's some terminology such as lax monoidal or something in that direction. And again, this is just what we already said. If neck cutting is possible for all manifolds n in dimension -1, then in fact alpha is multiplicative in a strong sense, so that these maps are isomorphisms. And then it's a TQFT in the sense of IT. If you also have this condition on, orientation reversal and additional involution in your field. So let us, before we give examples, let me just briefly mention the history of this. This is incomplete, but a key paper, the first paper I think where this appeared is by Blanchet, Haberger, Masbaum, and Bachel from 1995, where they studied this universal construction mostly in the context of Witten-Schetichen-Toraev TQFT for SL2. So they kind of quickly, they define the general situation, they quickly specialized to the multiplicative case in a strong sense and Witten-Schetichen-Toraev TQFT. Then in link homology, we often do something similar, especially in the link homology beyond SL2 case, where you can hide this universal construction. You can, yeah, I also, let me just mention that I refer to this kind of procedure getting state spaces for n-1 manifolds from evaluations for n manifolds. I call this universal construction. But in link homology, we do this all the time, but not for manifolds, but for forms. And I can say more about this at the end, but in link homology, to build maps within link homology groups in SL3 and more generally SLN theory, the way we do it, we introduce forms. We introduce planar graphs and build homology for planar graphs, and also build maps between state spaces for planar graphs assigned to forms. And state spaces, kind of in this way, the universal construction naturally appears out of forms for forms embedded in free space. So maybe I can say more about this at the end. And the key paper here is a work by Robert and Wagner, form variation formula from 2017. Then there is also work of Friedman, Kitaev, Nayak, Slingerland, Walker, and Wang, universal pairings from 2005, work of Calgary, Friedman, and Walker on the same topic, and several related papers where they discuss this construction in a special case when there are no relations on alphas for various manifolds. So in other words, you for each, instead of the field K, so the field K, you take a very large ring generated by diffeomorphism classes of closed, connected, oriented, and manifolds, so a fixed dimension n. So because alpha is multiplicative for the joint union, you restrict to connected manifolds, closed manifolds, and oriented manifolds up to diffeomorphism. So for each such diffeomorphism class, you have one generator of your commutative ring. And then you take the large polynomial ring over complex numbers on those generators. So that's a huge number of generators. They work over complex numbers. They add Hermitian condition on the Badinian form corresponding to the orientation reversal. And they ask whether the resulting Badinian pairing is universal in the sense that there are no relations on alphas for different manifolds. They ask whether it's positive definite. And then there is a difficult deep result that it's indeed positive, and it's indeed positive in dimension 3. And the original paper shows that it's not positive in dimension 4, but due to the existence of various smooth structures on homeomorphic for manifolds. And so you can think of this as a universal construction, but in incredibly special case, the case when there are no relations on alpha. Alpha is maximally generic, essentially. And today we're discussing the opposite case when there are lots of relations on alphas. So we want the state space to be finite dimensional rather than being this very, very large polynomial ring in the closed case. But it definitely fits the story in some cases. But this is a very sophisticated work where you have to use lots and lots and lots of results from 3D topology and techniques to show that it's positive definite, that there are no null vectors. And I'll tell you about very recent work from last year, where we look at toy cases of this universal construction in very low dimensions. It's interesting even in dimension 2, and it becomes especially interesting even in dimensions 1 and 2 when you add decorations to your n-manifolds. So you can add sort of submanifolds. You can add defects of various dimensions. You can decorate them. Potentially, you can add networks kind of to your manifold. So it gets very sophisticated or tricky even in low dimensions if you add decorations. This is one of the interesting points. So I'll tell you about joint work with Radmila Sazdanovich, Chiyo, Lev Razansky, Viktor Ostrik, Yakov Khovanov, Robert Logwitz. The last papers in progress. And again, they're toy cases up to dimension 2, but they're still interesting. And again, I want to point out that the story comes for now with a caveat, with a catch, that, I mean, it looks quite interesting, but for now, I don't think there are big applications, at least in those low dimensions, dimensions 1 and 2, but it's still interesting. So let us now, so I still need to give you a non-trivial example of this. And so let's go back to this construction. Again, we start by assigning numbers, elements of the field, to closed n-dimensional objects, for instance, n-manifolds. And then, given that assignment alpha, we build state spaces for n-1 manifolds. And so by construction, this is functorial. So given a cobordism M from n-1 manifold n-null to n-1 manifold n1, this cobordism M induces a map between the state spaces from alpha n-null to alpha n1. So namely, to build this map, take a manifold m-null with boundary n-null and compose it with manifold M to get a manifold M n-null with boundary n1. Of course, it's as usual in TQFT, so that's exactly what we do here as well. So compose with M. So in terms of symbols, symbol of m-null goes to the symbol of m-null. And this gets us, this descends to map of state spaces. So we get a map from alpha n-null to alpha n1. And so in this sense, this construction is functorial. Any cobordism induces a map of state spaces. And we get a functor from n cobordisms to the category, excuse me, in this example, to the category of vector spaces over a field K. Excuse me. And this functor is monoidal in a weak sense. Monoidal in the sense that given cobordisms m prime from n-null n1, from n-null to n1, from n-null prime to n1 prime. So if you put them next to each other, you get a cobordism M union M prime. So this induces a map of state spaces from alpha n-null to alpha n1. M prime induces a map of state spaces from alpha n-null prime to alpha n1 prime. And the union induces a map from the state space of n-null union n-null prime to n1 union n1 prime. And of course, the diagram commutes. So tens of these maps together include, that's the same as including, and then mapping using the union cobordism. Again, everything is kind of immediate here. Again, this is just like we're just saying that the standard features of TQFTs, they also work in topological theories that are not necessarily TQFTs. Okay, so now we can look at the first non-trivial example. Let us look at the case when n is equal to 2. So we're in 2 dimensions. Our map alpha is determined by its values on, well, n equal to 2. So we're dealing with surfaces. They are oriented, closed, and connected because alpha is multiplicative. So that means that alpha is determined by its values on surfaces of various genera G. So genus G can be 0, 1, 2, etc. For each genus G, we get a number alpha G, an element of K. So our theory alpha is determined by its values on the two sphere, assigning number alpha null on the two torus, alpha 1, genus 2, alpha 2, and so on. So that's a sequence of elements of the field, alpha null, alpha 1, alpha 2, etc. We can encode the sequence by its generating function in a variable t. We can write this sequence using our series z alpha of t, alpha null plus alpha 1t, alpha 2t square, and so on, which you can also write like this. So the data in dimension 2, the data is just sequence of numbers of elements of K. So now given this data, how do we build the state space for a single circle? Well, a single circle, so you have a cobordism. That cobordism can have some components that are closed. Those components can be evaluated right away and just converted to corresponding numbers. You can evaluate them using alpha, convert to numbers, and just reduce to a cobordism, which is connected with one boundary component. And then this cobordism is determined by its genus 0, genus 1, genus 2, etc. So they can reduce the state space to have a spanning set of vectors v null, v1, v2, vn, one for every genus. So v sub n has genus n and one boundary component. And so this picture sort of shows you that in this universal construction, if you have a closed component for your manifold, you can just evaluate it using alpha. And in this example, the evaluation is just alpha 2 because of genus 2. Now, what's our bilinear pairing for this v sub n's? Well, if you couple v sub n to v sub m, this is vn, vm, we do them together, we get a closed surface of genus n plus m. So its evaluation alpha is alpha n plus m, is the number we assign to n plus m. So that's it. This is our pairing. So we have these vectors, v null, v1, v2 infinitely. This is our symmetric bilinear pairing. So we should just take the kernel of this space with this basis, kernel of that space by this pairing, by the kernel of this pairing. So the pairing in matrix form as follows. So the inner product of the ivj is alpha plus j. So if you write genera as rows and columns, then on the intersection of row I and column j, we have alpha plus j. So you see we get a matrix of the bilinear form, the gram matrix, which has each diagonal carries the same number. Each of the diagonals carries the same number, alpha null, alpha 1, alpha 2, etc. And matrix of this form with entries along the diagonals the same is called the Hankel matrix. Called H, it's n by n matrix. And our state space of a circle is the quotient of a vector space with basis Vn by the kernel of this matrix, so by the kernel of the bilinear form given by this matrix. And of course, this is it. And of course, in the generic case, if we kind of if you don't try to impose any relations on alphas, just pick random alphas, there'll be no kernel. And that means that the state space will just be will have a basis v null, v1, v2 with no relations. And of course, that's not very interesting. And we want the kernel of H to have finite codimension in that vector space, which I write as k to the n with this basis. And if it has finite codimension, then dimension of I call this A1, just the state space of a circle. A1, just another notation for alpha of S1 for the state space of a circle S1. let's see if okay, there's a theorem here. So you can ask when will it be, when will the space have finite dimension? So the point is that what you'll need is that you need to have some R, so that the first R+1 vectors span A1. And beyond this, you want to have linear dependence. Now, R means that you have R handles. Once you go beyond R, you'll have R+1 handles. Okay, so what you want is a dependence where you can remove a surface with R+1 handles and boundary one circle. And so let me state the theorem that essentially goes back to Kronecker, to the 19th century, but we can phrase it like this. So the following are equivalent. The state space of a circle has finite dimension. The state space of M circles, here AM denoted by M, the state space of M circles. So you have M circles, look at all the cupboards, at all the manifolds that bound in circles, modular relations. So this happens if and only if this happens for all M. This is very easy to see. It's very easy to see. In terms of this happens if and only if the generating function is a rational function. Of course, that's a very strong condition, because here we just have, here we have power series in T, it's almost never rational. So the theorem says that the state space is a finite dimensional if and only if this power series is a rational function in T. So it has the form polynomial divided by a polynomial. And you can, it's not hard to prove. And again, so the idea is that the condition 1 tells you that you can reduce R+1 handles to a linear combination of fewer handles, of surfaces with fewer handles and the same boundary. And once you have this relation, you have a dependence. You'll have a dependence on coefficients of Z alpha starting from this many handles, starting in that degree. And this in turn will tell you that the generating function is a rational function. Okay, I still want to get to an example. Let me see let me actually kind of first say general case. What happens beyond a single circle when you have a state space with for 2 circles, for 3 circles, etc. Beyond a single circle, when you have 2 circles, of course, you have the inclusion of the tensor product of 2 state spaces. For a circle, just put the surfaces next to each other, surfaces with boundaries 1 and S1, put them next to each other to get a surface with boundaries 1 union S1. But you might be missing something. You might be missing cobordisms of this form, just a tube cobordism between 2 circles and the tube cobordism with some number of handles. Tube cobordism with some number of handles. These elements are they are in A2. They are potentially not in A1 tensor. A1 sitting inside A2. So these are additional elements, additional vectors in a state space. So usually this is bigger than the tensor product. And beyond this, so for A3, you can, when you have a cobordism with boundary 3 circles, it can be connected, or it can consist of connected components. And these connected components will give you a decomposition of the set of boundary circles into subsets, where you just have one subset for every connected component. So for this picture, you'll have connected component which contains circle 1 and 3, and component that contains circle 2. For this cobordism, you have 3 subsets, 1 for each circle. So you, given a cobordism, you can assign to it a saturated partition of the union of circles. And so if you already know that A1 is finite dimensional, then that tells you that you can reduce R+1 handles or more handles to fewer handles. And then you can always reduce so that on each component you have at most R handles. no greater than R. And once you know this, if you know that each component carries at most R handles, up to this equivalence in the quotient space, and once you know this decomposition into connected components, then you can get an upper bound. You can get a spanning set just for each possible decomposition into subsets. You can put any number of handles, but at most R handles here, at most R handles here. And in this way, you get an upper bound on the size of a state space for M circles. And then once you know that it's finite dimensional for a single circle, you can conclude that it's finite dimensional for any number of circles. And this is a simple way to see the equivalence of conditions 1 and 2. So this implies 2, and of course 2 immediately implies 1. Okay, so let us now get to an example. So for example, we take our generating function to be just a constant function. So we choose beta, an element of the ground field, not 0. And for simplicity, let's take field of characteristic 0. So for this particular generating function, the evaluation is as follows. So sphere evaluates to number beta, but anything of high genus evaluates to 0. So genus 1, genus 2, etc. evaluate to 0. And in particular, this means that we have this handle relation. So when we have a torus with one boundary component, that evaluates to 0 no matter what we attach, because anything of genus 1 and higher evaluates to 0. So we have the skein relation. Again, it's a feature of a special example. And because we have a skein relation, we see that the state space of a single circle, we can reduce it to just one vector, because anything of high genus is 0. So the state space of a single circle, in fact, it's just one-dimensional vector space with this basis given by the disk. And so again, we see that using this relation, we can reduce to the case when each component has genus 0, no handles. So let us now look at the case of two boundary circles, A2, state space of two circles. It has this spanning set, just a tube and two disks, because we're down to genus 0. So these are the only possibilities. To see if it's a basis, we write down the gram matrix of the bilinear form for the spanning set. So two vectors here, two vectors here. Go ahead. Is that a question?
Well, excuse me, I have a question. Usually when we have irrational functions, it's very good for counting something in combinatorics. So for counting some objects. So can we somehow use any TQFTs to solve problems of combinatorics and vice versa?
Yeah, so it's a good question. It's a good question. I don't know. Sometimes you encounter a lot of power series in combinatorics also. Of course, for power series, the state spaces are infinite. So the short answer is I don't know, but I think it's a very good question. Whether you can match some generating functions in combinatorics to these generating functions in some cases. So let us now look at this bilinear form for the spanning set. So for each of these manifolds, we pair them. So we kind of flip. Let's see, we flip this manifold to the other side and glue it to this manifold. So as this entry, we get two spheres. Now for this entry, so we flip this to the other side, glue to the tube. We get a two sphere. Now this matrix is symmetric. So we have a two sphere here. For this entry, we take a tube, reflect it, and glue to this tube. We get a torus. So this is then our matrix. And we need to apply evaluation alpha to every term. We apply alpha. There's like two spheres. We get beta squared. This is a two-sphere beta. Here we have 0 because alpha of a torus is 0. So then this is our gram matrix. And you see that this gram matrix has non-zero determinant, minus beta squared. So this tells us that the set of these vectors is actually the basis of A2, not just a spanning set. That's the basis. And we also see that the inclusion from A1 squared into A2 is not an isomorphism. This inclusion misses this vector. So it's an inclusion of a one-dimensional space into a two-dimensional space. So this example is not a TQFT. This is not on the image. So you can play with this. You can look at the state space of 3 circles, A3. It has this spanning set. But again, because we can get rid of hygienes. And you can compute the determinant in this basis. And you get off the gram matrix 5 by 5. And you get the determinant to be 2 beta squared. So if characteristic of K is not 2, in fact, it's a basis. So if you go further to 4 circles, then you get a spanning set of partitions, theoretic partitions of 4, like here. So here we look at all possible ways to break, to kind of decompose the set of 3 elements into partitions, theoretic partitions. And for 4, you get 15 partitions. So actually, some of them are here. So this is partition 1, 2, 3, and 4. This is partition 1, 2, 4, and 3. This is partition 1, 4, 2, 3. So you get 15 elements. You can look at the gram matrix. Gram matrix has size 15 by 15. And you can check that because once you have a component of genus 1 and higher, it evaluates to 0. So the whole thing evaluates to 0. Because of this, you can check that in your matrix, you get an 8 by 8, a block of zeros. You can kind of check that you'll have lots of zeros, and you can arrange them. You can arrange some of them. I'll draw it here. So you'll have a 15 by 15 matrix, and you can arrange. You can arrange this matrix to have a block of 8 by 8 block of zeros. And as a result, you have a relation in the gram matrix. So the vectors are not bases, determinant is 0. And you can write down the basis, you can write down the relation easily. Well, the relation ends up being this relation. It's a relation on 8 vectors, 8 vectors out of 15. And it's invariant under the action of the symmetric group S4. So if you look at these terms get permuted by the action of S4, by cobordisms that permute the circles. So if you apply this cobordism to this surface, you get this surface. So you'll have elements in the orbit of S4 come with the same coefficient, in this case 1. These 3 elements are in the same orbit, in one orbit of S4 action. These elements are in one orbit of S4 action. So permuting this 2 will give us this element. And this element is in an orbit by itself. So you can think of it as a linear combination on 8 vectors in the spanning set of A4. And this combination is invariant under the S4 action. And then this is the relation. We get beta here. One thing you can do is notice that in this picture, everything looks flat if you draw it as pictures on the plane, except for this term, which has a crossing. So we have these surfaces, thin surfaces, that we drew using the projections onto the plane, and all of the surfaces are in some sense flat. They kind of look flat. I'm not trying to make this kind of accurate, but I mean, I think you can see what I mean from the picture. but this surface has a crossing. So what that tells us, that if you draw everything in this flat way, then we can inductively simplify crossings until there are no crossings. So we can, in the state spaces for any number of circles, we can get rid of all the crossings. So we can reduce to these flat surfaces, each one of genus 0, because any handle is 0. So that's what we say here. We can get rid of all crossings and reduce any element of the state space AN to a linear combination of what we call genus 0 crossingless surfaces. This is a picture of a genus 0 crossingless surface. And once you define this rigorously, you see immediately that they are in a bijection with crossingless matchings of two endpoints. N is the number of circles. If you take this surface, this kind of nice surface, you cut it by a plane. In the cross section, you'll have 2 points left from each circle. And then, for instance, this disk will become an arc. This sphere with 3 holes will become a collection of 3 arcs. And then you get a bijection between such surfaces and crossingless matchings. Crossingless matchings of 2 endpoints by arcs in the lower half plane. So given such a crossingless matching, you just color it in a checkerboard way. So shade every other region. And then, so you take the shaded region and thicken each of them to this kind of handle body with, or to this, in fact, 3 ball with of a special type of kind of boundary, with boundary disks on the top plane and boundary spheres with holes inside. So thicken this way. And so you get the bijection. And there's a theorem from a recent paper by Yakov, Khovanov, Viktor Ostic, and myself. So in fact, in characteristic 0, state space AN is a vector space given with a basis of crossingless surfaces. So such surfaces give us a basis. And the dimension of the space is the nth Catalan number. And so this is for a very particular, very special generating function that is a constant, so no high terms. And the proof is based on computing the determinant for this Gram matrix due to Yakov from a paper joined with Yakov, Kichlu, in progress. And it's a modification, it's a slight modification of the meander determinant due to Di Francesca and his collaborators. And there's also relation to representations of OSP12, another way to get this formula. So this is an example in dimension 2 where the generating function is a constant. And it gets quite interesting even in this case. And the state space, as we mentioned, the state spaces are not multiplicative. You only have inclusions from the state space. Let me see if I mention this below. We only have inclusions. Instead of 1 and 1, you can put here little m, and n plus m here, and you'll only have inclusion. So maybe it's a good time to take a break for 5 minutes, answer questions.
Okay, dear colleagues. So possibly there are some intermediate questions. So are there any questions to the speaker? Well, if it's not the case, so let's relax for 5 minutes. And
sorry,
okay.
May I ask a quick question?
Sure.
So the work so far is in very low dimension, and it seems lots of explicit combinatorics is involved. I'm curious if this is possible to be generalized to like even 1 dimensional higher.
So you'll get I mean, so you get more complexity even in low dimensions if you add submanifolds. If you add decorations, I'll tell more about this later.
Huh.
In dimension 3, it's very hard. So one in dimension 3, it's very hard. It just hasn't been studied beyond those papers of Friedman, Kevin Walker, and their collaborators, Calgary. So the case, the kind of the opposite case when there are no relations on invariance for different manifolds, it's this paper by Calgary, Friedman, and Walker. That's so it's quite complicated. So they prove positivity of this invariant for 3 manifolds, but I mean it's quite involved.
But is their result as explicit as yours?
They prove that the result implies that the state space, that the result, so it implies null vectors. Yeah. So the result is that there are no null vectors in dimension 3 if you use the theory with alpha that's maximally generic, no relations between multiplicativity, and you use complex numbers so that you have positive definite bilinear form, so that you have a Hermitian form. And they show
Okay, I see. Thank you.
Yeah.
Yeah,
Yeah.
Any
In
further
dimension 3,
questions?
it might be. Yeah, I mean, I guess we.
Okay, so let's make a short break.
Yes, so in dimension 3, it might be interesting to study the state spaces, even for. So you need to pick an invariant. You can pick an invariant of 3 manifolds. You can ask, for instance, which invariants will give you fine dimensional state spaces. This might be a hard problem.
18:30. Что еще, что 19:30?
I don't know. There's some. I'm not sure if is there a question. Is there a question from Sergey? I cannot say. Can I figure it out? Yeah. Yes. So I think dimension 3 is completely unexplored. So you can just ask it first, for instance, for examples of the spheres that are not TQFTs, that are not the classic examples coming from Witten-Stichen-derived TQFT or Dijkgraaf-Witten TQFT. You can just ask for more examples, find some examples that are not TQFTs, and also give you finite dimensional state spaces.
Right,
that's a good question. You can also do it just for nodes and links in R3 because that brings the complexity down. You can restrict.
Ну, я уже видел это.
So for 2D, we really use the classification of surfaces. But for 3D,
it's much. As I said, it's much harder. So it's, for instance, it's hard to. I think it's one of the first questions would be, can one find examples with finite dimensional state spaces that are not TQFTs, where the invariant is not multiplicative in a strong sense, when the state space of a union is greater than the tensor product of the state spaces of each piece. I think this is already a non-trivial question. But also in dimension 3, you can look at case of just links in 3 space. When you look at links in 3 space, if you cut it, so you have numbers assigned to nodes or links in 3 space, and then you can get state spaces. What are the state spaces of? Well, if you cut it by a plane, you see 2 endpoints in the plane. So it's a state space of 2 endpoints. Well, given in a similar way. So you look at all the tangles on one side that bound 2 endpoints, take the linear combinations of those tangles, modular bilinear form, modular scaling relations. So can one find examples that are not multiplicative, but have finite dimensional state spaces?
But not multiplicative, do you mean not surjective or something more?
Well, I mean, of course you can, you can probably, because you're not using, you can probably just take, I think if you take the usual quantum invariants of links, they're not necessarily multiplicative because you're only picking some subspace in the tensor product of representations, you're picking just invariants. So in this sense, it's not multiplicative, but you can extend it. You can complete the tensor products to get a multiplicative state space. But you can ask, what are examples beyond some standard ones coming from quantum groups?
Okay, thank you very much. So I think if everyone is ready, so possibly we may resume our talk. I think it would be okay. So I think you have more than half an hour, maybe. Well, everything
Okay,
is up to you.
I can definitely finish in half an hour.
Yeah. Okay. So let's resume. Okay.
So let me go back to my notes. Let's see. Oh, can you see? It says
not yet. Not yet.
Okay, I can try again. Oh, now I can see. Okay, now you can see. Okay, so now it's okay. Yeah, so let us discuss the examples beyond the constant function. So in general case, to get finite dimensional state spaces, we want a polynomial. Also, we want a rational function, polynomial by the polynomial. I had some there's some confusion, maybe notations, because on this page I use capital N, capital M to also denote degrees, and before we used them to denote manifolds. So I hope this won't lead to confusion. But on this web page, in this page of slides, N and M denote degrees of the numerator and denominator polynomials for the generating function. So take this N and M, and so I'll tell you the answer, how to get the relation on handles, and take the max of M of the degree of denominator and max of N plus 1, degree of numerator plus 1. And in fact, this K is equal to degree of the denominator exactly when P over Q is a proper fraction. So degree of P is less than degree of Q. We can normalize so that Q of 0 is 1. And Q has this form. Polynomial Q is 1 plus other terms with some coefficients up to degree M. And again, P over Q is this rational function, this power series. So now with these coefficients betas for Q, we can check that for any P given Q, we'll eventually have this scale relation. So we'll have this recurrent relation on alphas. So alphas, this is in the denominator and we expand. So you can check that alphas will have this relation. So alpha in some high degree, M plus lowercase m, plus B1 alpha in 1 degree less, plus B2 alpha in 1 coefficient, in 2 coefficient less, etc. Plus Bm alpha n is going to be 0. This just follows from the expansion. For sufficiently large n, depending on P. So eventually we'll see the same recurrent relation on alphas, but not right away. Yeah, sort of this n depends on degree of P. So if degree of P is less than degree of Q, you actually have it right away. You can take n equal to 0 to get a skein relation. But for degree of P greater than degree of Q, you have to pick a suitable n to have this relation in large degrees. And just one thing to note is that the kind of order of betas is reversed compared to Q of T. In Q of T, in the denominator, these betas, they increase as the degree increases, but here they increase as degree decreases. but again, it's immediate from the manipulation of the generating function. And if degree is less than q, degree of p is less than q, then in fact this holds for all lowercase n. And otherwise you need to, one way to think of it is that you can take the ratio p by q, write it as a proper fraction with p tilde over q, degree of p tilde less than degree of q, plus polynomial in t, r of t. And then having this polynomial kind of doesn't allow you to have this recurrent relation right away. So you need to take sufficiently large n to avoid coefficients of RT appear in this formula. This is the explanation for why you cannot always start at the lowest, in the lowest degree. So because of this presence of this polynomial, when you write down the relation on handles, the scaling relation on surfaces that bound a circle, you need to add this offset term, which is the difference in degrees, degree of p plus 1 minus degree of q, k minus n. So it's essentially you to write down this handle polynomial, the scaling relation on powers of a handle, you take q, t, you reverse it. So now b's go in the opposite direction. And if necessary, you multiply by this offset term, power of x, to take into account that you might get sort of, so to speak, garbage before you get some garbage that doesn't know about q of t, before you can use this recurrent formula.
Well, excuse me, one more question. So in combinatorics, we often see lots of nice recurrent formulas, well, Fibonacci numbers, Catalan numbers, or whatever numbers with the nice denominators and other things. And of course, combinatorials often ask questions. If we have natural numbers, then they should count something. And well, of course, so addressing to the author of categorification, if they count something, then can we categorify this something? So instead of counting, can we make it into dimensions of topological objects? So if we have just some ratio of two polynomials.
Yes, I think it's a great question. And of course, I think that there are many authors, so you should ask maybe Igor Frenkel and Louis Crane. And you can definitely look into counting, and then maybe it's going to be related to summing in high dimensions on one side, but also so I'll give you some references, which is, I mean, it's not maybe exactly, doesn't answer your question exactly, but it sort of explores in a maybe related direction. So let me just finish with the handle polynomial. So given the generating function z, which is rational, we can pull out of it this handle polynomial, and then the result, the immediate result, is that we have the following handle relation in the state space of a circle, namely that polynomial ux is 0, where x is a handle, and x to some power means power of the handle. So this is x squared. Here you'll have x to the, if you multiply out, you get x to the k. X to the k can be expressed as a linear combination of lower degree terms. So let me give you an example. So if you were to take this generating function, it's a rational function. So the degrees are the same 2 and 2. And because it's not a proper fraction, there is an offset term, which gives this x. And we also take the denominator, and we write the reciprocal polynomial. So here it's 1 minus 3q, here it's 1 minus 3q in the opposite direction. So this is our handle polynomial, and this is our handle relation, which says that x cubed is a linear combination of x squared and x. So 3 handles going to be a combination of 2 handles and 1 handle, and that's a scaling relation. There is no constant term, well, because of the offset because it's not a proper fraction. And this is how to get how to get the scaling relation from the generating function. So there are some additional structures. So for instance, A1 is a commutative Frobenius algebra, because A1 elements here are represented by cobordisms by surfaces with one circle component. So taking two such surfaces and composing with pens gives us an element in the same space. So for this reason, A1 is a commutative algebra, it's Frobenius. So some things are similar to 2D TKFT, some things are different, in the sense that this is just an inclusion, not an isomorphism.
So what about the SN action? Is it inside the rule of the game, or we can do without?
It's part of this. It's part of the story. You have SN action on the state space of n circles, just because you have permutations of circles. So it's part of this story.
Okay.
And maybe again, it's not exactly, it doesn't exactly answer your question, but I want to point out many connections to algebra. So these relations, the relations that we have here on coefficients are known as linear recurrence relations. And there's substantial literature on them called LRS for short. So they studied a lot. They have various connections to number theory. As an example, as a teaser, I can give you, so I haven't explored, I don't know if anyone has explored possible relation between this LRS and topological theories, but just one example of an interesting phenomena is the result by Skjold, Muller, and Lech, saying that in characteristic 0, if you take the union of all indices n such that alpha n is 0, where the function is a rational function, where z alpha t is a rational function, and it's always a union of finite set and finitely many arithmetic progressions. But it fails in finite characteristic for infinite fields. But so there are various properties of this linear recurrent sequences, and it would be interesting to see if there is kind of some interpretation of those on the level of topological theories. This is just some references for linear recurrent sequences and generalizations. There's a book by Everest et al., Recurrent Sequences. If you look at various books on finite fields, they discuss linear recurrent sequences a lot. And as I understand it, at the dawn of computation, at the dawn of cryptography, people would use linear recurrent sequences over finite fields as a way to produce sort of pseudo-random sequences, well, in a naive sense, with very long periods. So if you use a finite field and some kind of random rational function, then you can get the sequences that sort of look like quasi-random for a while. So this is one reference. Also reference for the sequences and non-commutative generalizations that come up in topological theories as well is a book by Berstl and Reutenauer, Non-Commutative Rational Series. It's a classic book on the subject. So let me see. So maybe I can skip. I can skip the sort of categorical framework. Let me skip a couple of pages and instead go. Let me tell you a little bit about dimension 1. So I want to say that we've looked at this last year in several toy cases. We look at 2D case with boundaries, sort of and corners. This is work joint with Chi and Lev-Rozansky. In the same paper with Yakov Khovanov and Viktor Ostrich, we look at 2D where you add zero-dimensional defects, but we haven't looked at examples, so just possible framework. So most of these papers just set up frameworks. The examples are only worked out in this paper, in the 2D case. But I want to, in the remaining 10-15 minutes, I want to tell you about 1D case with defects. And 1D case sounds rather trivial. So in 1D case, we just have one manifold. But here we do an example where our manifolds, our cobordisms have defects. So if we had no decorations, if you have a closed one manifold, it's a union of circles. Then to a circle, we would assign some number, some element of our ground field. Then to a union of k circles, we assign that number to the k, and that's our data. So our data, our theory just depends on a single element of the field. You get something, you essentially get a version of the Brouwer category with that parameter, which has been well studied. But you can do much more if you add decorations, if you add defects. So what we do, we add on our one manifold, we add dots at the zero manifolds, and we label them by elements of a set S. Set S is sort of set of defects. So we put label, which is an element of S, for example, B, A. And so in this way, our cobordisms now carry these defects. And if you look at closed cobordisms in dimension 1, it's a union of circles. And now circles come with this sequence of labels AA, B, C, AB, which sort of tells us what the defect is. And in this example, and so to this circle with defects, we assign a number, an element of the ground field. And as this assignment function, I call it again alpha. Alpha takes this data of a circle with a sequence of defects and assigns a number in k. And in this example, we can start anywhere in the circle. So if we start here and we see AA, BC, AB, you'll see this sequence. But if instead we start here, we see A, B, C, C, so you see the sequence. So sequences that are related by cyclic permutation should give the same number. So this is an example, ignoring the cyclic condition. This is an example of non-commutative power series. So this alpha. So for alpha, we now have a lot of freedom to every sequence to every word, to every sequence of labels from the set S, we assign a number in the field. So that's lots of flexibility. In this example, the assignment is symmetric under cyclic rotation. We still have exponentially many assignments if we were to fix the number of dots. So there's still lots of possibilities. And we encode our theory by what people call non-commutative power series. And this is just a formal linear combination. We take infinite sum over all words, over all sequences of elements of S, all sequences omega, times the coefficient times the weight of the value of a circle labeled by omega. And this is known as non-commutative power series. In our example, it's symmetric, but it's easy to modify the story by adding defect intervals. By adding cobordisms that can end in the middle to dispense with this condition that things are symmetric. But in this case, you get into the theory of non-commutative power series. So for instance, when you look at the state space, if you were to look at the state space, say of 2 points, put here plus and minus. So take an interval oriented, put your sequence here, A, B, A, C, etc. For the state space for these 2 points, plus and minus will actually be something that Reutenauer introduced as syntactic algebra. Syntactic algebra of series alpha. But we have a little bit more. We have more general state spaces. We can have scaling relations that involve several components. there was a little bit more than just symplectic algebra. So you can think of using the story to build some kind of tensor envelope of symplectic algebra and of non-commutative power series. And there are also interesting connections to just computation, to finite state automata, if you change from ground field to ground commutative summary. And so it's a kind of separate long story. And so the entire theory of non-commutative power series came out of study of finite state automata back in the 1960s, 1970s by Schutzenberger, Quinn, and other people. So you can find kind of canonical books by Eilenberg, by John Conway on the study on finite state automata. And later this developed further into non-commutative power series by Schutzenberger, Riotenauer, etc. And sort of this connection, I mean, supposedly new connection to topological theories is that we're now able to, on one hand, look at some kind of, so to speak, tensor envelope, this topological theory, that gives you a little bit more information than just what you get by traveling along a line in the story. You get a syntactic algebra, but it's also worth exploring the, I think, in high dimensions, the connections between this topological theories and computation in the generalized sense, because this is just in dimension one. Sort of conceptually, the appearance of finite state automata corresponds to the following fact: if you were to look at the state space of this plus and minus, maybe I can draw it here. So you have a state space of plus and minus zero manifold. Its state space, let me call it say vector space V. This map will correspond to inclusion of the ground field into V, and you can compose with cobordisms where you can attach one of the elements A of your set of defects S, and this element A will give you a map from V to V, map multiplication by A. Let me call it, say, M sub A. Then you can compose with, say, B, get a map from B to V, multiplication by B, and so on. And so you can get a long sequence here. And eventually you're gonna compose close up using a map back into the ground field. This is I, this is epsilon. So if you look at what you have on the algebraic level, you have inclusion of the field into vector space V, I. You have a trace map from V back into the field epsilon. And inside V, you have linear maps and dimorphisms, one for every element of the set of labels. And this is a linear version. This is a linear version of finite state automata. In finite state automata, you have states and you have transitions that depend on the labels you read off your word. And this is a similar situation, but instead of a finite state of states, you have vector space of states that's finite dimensional. Then you have you can enter it and later exit, and for each product, A, B, A, B, A, etc., you get a number, alpha.
So do you mean that you categorify the notion of auton-auton?
No, you just, we just saying that if you look at what happens in the one-dimensional case with defects, like for this particular cobordisms, then you can match this to the notion of what people call non-commutative and C rational power series. Rational power series, it has several equivalent descriptions. One of them is that it's a series. One of them is that alphas, the evaluations alphas of words can be encoded in this way, that there is a finite dimensional vector space, these maps and these maps, such that alpha for any sequence t, alpha of t is equal to I composed with this map MT, so map composition of maps for elements of a sequence T composed with epsilon. So for any word T, I guess we called before words omega. So that alpha is a sum, let's say alpha T times T, or a sum over words T. So there are several equivalent notions of finite state automata, and you can think of it as linear finite state automata, linear over K. This is one possible definition. And then you say that non-commutative power series alpha is rational if alpha given by this expression, it's rational if such a system exists with vector space V with inclusion, evaluation, and linear maps MA in it. So this is one of the ways to define what it means for the non-commutative power series to be rational. One of the ways. But if you change from K field to K Boolean summaring, 1 Boolean summaring B summary, so that 1 plus 1 is 1. It's not a ring. Then you recall the notion. Then if you look at what this means in the Boolean summaring B, you get the notion of finite state automata. To kind of picture-wise, you're an automata, but now closed cobordisms evaluate to elements of a semi-field. In this example, Boolean semi-field B. But so was kind of cute link to computation. So the sort of the classical computation in the toy case of finite state automata can be managed to just kind of traveling along this line in a 1D cobordism, reading off these labels, and kind of moving inside this, well, in the computational case, not a vector space. It's going to be a set of states with transition maps for all labels. But again, this is just 1D case with difference, but we already see connections to non-trivial subjects, non-commutative power series, automata. So it's quite interesting. So let me stop here. Thank you.
Okay, thank you very much for a really great talks, dear colleagues. Please ask your questions right on the chat line and mute your microphones. So we have learned so much today. Well, actually, I have a question. So our seminar is now in the middle of creating non-commutative invariants in the following sense. We try to count some points in some moduli spaces and make them into, I would say, make them into words in non-commutative groups. So actually, we have lots of invariants, and they are valued more or less either in free groups or in pictures. Pictures, something like node diagrams. So I think it may be used more or less in any of your settings. I mean, so if you want to have graphs, we can try to categorify it, but in some other sense, not by associating vector spaces, but by associating pictures or something non-commutative, which resembles node diagrams. So actually, I want to see whether we can find something of close interest here.
Yeah, so it would be interesting to compare. But if you have something written up on that, if there are some papers, can you send me I mean, if you can send me a link.
Sure,
I
sure.
also want to mention that.
Of course.
Let me see. For
and
for
the main dream is to make all mathematics non-commutative. The main dream is to replace characteristic classes with, say, characteristic loops or intersection points with non-commutative things.
I want to say, but definitely, I mean, one reference to non-commutative. So this is the classic kind of reference. It's a book. You can find it online for non-commutative power series. So you can maybe explore it in relation to your work, but also, of course, it kind of closely relates to what I discussed in dimension 1. I mean, I can, for connections to low-dimensional topology, there is also a paper by, I think it's Weintraub, Reutenauer, and Vladimir Retach. They have a paper on non-commutative power series in relation to three-dimensional invariance. I forgot the exact name. So Retach has, I mean, he's a major force in non-commutative story. So he has many papers, but definitely I want to, since you mentioned your explorations, I want to, I mean, it sounds like maybe this is a paper you want to look into at some point by Weintraub, Reutenauer, Retach. And on a more fundamental level, and on a more basic level, and general level, I definitely, this is also a book that I want to explore more by Bersel and Reutenauer on non-commutative rational series. I think it's called maybe non-commutative power series. I forgot the exact name. It's very easy to find. Yeah, and so these books, they explore recurrent sequences, but just linear recurrent sequences, not so the usual commutative case, not non-commutative case. But this is kind of a separate question. However, this story that I told you about has kind of something interesting on the number theoretical side.
Great, thank you very much. Colleagues, are there any further questions, remarks, comments? Well, okay, let's end this. Yes, yeah, we would be very happy to.
Because I had a little bit of writing at the end,
yes,
compared to the original version.
Yes, sure. Please send us everything.
Thank you for having me and the opportunity to give a long talk.
Yeah. So this was really great. So thank you very much for having an opportunity. Soon we will have a conference, online conference, and Mikhail kindly agreed to be a plenary speaker at this conference, and we will be happy to see you again in a couple of weeks or so. I mean, topology.
So I'll talk about something else, but related. I'll talk about form variation.
Okay, thank you very much. Thank you very much.
Thank you, Vasily.
Okay, thank you.
Okay.
Thank you everyone for coming. Okay.